Hey there, fellow electronics enthusiasts. Let's talk about the building blocks of our digital world semiconductors. These amazing materials are neither good conductors like copper, nor insulators like rubber. They're somewhere in between, and that's where the magic happens. Semiconductors like silicon and germanium form the foundation of diodes and transistors, the unsung heroes of modern electronics. These little wonders control the flow of electricity in countless devices, from smartphones to spacecraft. Without them, our world would be a much quieter, less connected place. Think about it. No computers, no internet, no video games. So buckle up as we dive into the fascinating world of diodes and transistors, the dynamic duo of electronics. Let's start with diodes, the one-way streets of the electronics world. Imagine a one-way sign for electrons. That's essentially what a diode does. It allows current to flow freely in one direction, but blocks it in the other. Pretty neat, huh? The secret sauce behind this unidirectional behavior lies in the p-n junction. This junction is formed by joining two differently doped semiconductor materials, p-type and n-type. Think of it like this. The p-type has a surplus of holes, which are like empty seats for electrons, while the n-type has an abundance of free electrons eager to fill those seats. Now, let's talk about how we can control the flow of current through a diode using something called bias. Biasing a diode is crucial in determining how it will behave in a circuit, and it can be done in a couple of different ways. There are two main ways to bias a diode: forward bias and reverse bias. Each method has its own unique effect on the diode's ability to conduct electricity. Forward bias is like giving those eager electrons a clear path to those empty seats. Imagine a crowded theater where everyone wants to find a seat. Forward bias makes it easy for them to move towards their destination. We connect the positive terminal of a voltage source to the p-type side and the negative terminal to the n-type side. This setup creates an electric field that reduces the potential barrier, making it easier for electrons to cross over. This setup encourages the electrons and holes to move towards each other, effectively shrinking the barrier between them and allowing current to flow. The result is a smooth and efficient flow of current through the diode. Reverse bias, on the other hand, is like setting up a roadblock. Imagine trying to drive down a road only to find it blocked off. Reverse bias creates a similar situation for the electrons. We reverse the connections, pushing the electrons and holes away from each other. This action increases the potential barrier, making it much harder for electrons to move across the junction. This widens the barrier between them, effectively blocking any significant current flow. In reverse bias, the diode essentially acts as an insulator, preventing current from passing through. This property is useful in various applications where controlling the direction of current flow is essential. Diodes have some fascinating characteristics that make them so useful. One crucial characteristic is the forward voltage drop, typically around 0.7 volts for silicon diodes. This means that a diode will drop about 0.7 volts when current flows through it in the forward direction. Another important characteristic is the reverse breakdown voltage. Remember that roadblock we talked about in reverse bias? Well, if we crank up the voltage high enough, the barrier can break down, and a large current can suddenly flow in the reverse direction. This can damage the diode if we're not careful. Section 5. Diodes in action, from rectification to protection. Now let's get practical. Diodes are fascinating components that play crucial roles in various electronic circuits. They might be small, but their impact is immense. Diodes are everywhere in electronic circuits, performing all sorts of cool tasks. From simple rectification to complex protection mechanisms, they are indispensable. One common application is rectification, which is converting alternating current or AC to direct current or DC. This process is essential for powering many electronic devices that require a steady DC supply. Think of AC as a wave that goes up and down, while DC is a steady stream in one direction. This analogy helps us understand why converting AC to DC is so important for consistent power delivery. Diodes act like one-way valves, allowing only the positive or negative half of the AC wave to pass through, effectively converting it to DC. This selective passage ensures that the current flows in a single direction, making it suitable for various applications. Diodes are also great for protecting sensitive circuits from voltage spikes. These spikes can occur due to sudden changes in the power supply or external disturbances, and diodes help in mitigating these risks. Remember the reverse breakdown voltage? This is a critical parameter that defines the maximum reverse voltage a diode can withstand before it starts conducting in the reverse direction. We can exploit that by intentionally designing circuits where the diode will only conduct in case of a voltage surge, diverting the excess current away from the delicate components. This way, diodes act as guardians, ensuring the longevity and reliability of electronic devices by preventing damage from unexpected voltage spikes. Section 6. Transistors, electronic gatekeepers. Now let's move on to transistors, the real heavy lifters of the electronics world, performing crucial tasks. While diodes are like one-way streets, transistors are more like electronic gatekeepers, controlling the flow. They can amplify weak signals, switch currents on and off, and act as miniature amplifiers in circuits. Transistors come in different flavors, but the two most common types are bipolar junction transistors, or BJTs, and field effect transistors, or FETs. Both types have 3 terminals, but they control current flow in slightly different ways, each with unique characteristics. Section 7. BJTs and FETs, 2 flavors of control. BJTs are like current-controlled valves. They have 3 layers of semiconductor material, either NPN or PNP. And a small current flowing into the base terminal can control a much larger current flowing between the collector and emitter terminals. FETs, on the other hand, are like voltage-controlled valves. They have a gate terminal that acts like a tiny electric field, controlling the current flow between the source and drain terminals. By applying a small voltage to the gate, we can control a much larger current flowing through the transistor. Section 8. Transistor characteristics, gaining control. Just like diodes, transistors have key characteristics that determine their behavior. One crucial characteristic is current gain, which tells us how much the output current changes for a given change in the input current, for BJTs, or input voltage, for FETs. Another important characteristic is the threshold voltage, which applies mainly to FETs. This is the minimum voltage that needs to be applied to the gate terminal to start turning the transistor on and allowing current to flow between the source and drain. Section 9. Transistors at work, amplifying and switching. Transistors are the workhorses of countless electronic devices, thanks to their ability to amplify and switch electronic signals. In amplification, a small input signal applied to the base, in BJTs or gate, in FETs, can control a much larger output current, effectively amplifying the signal. In switching applications, transistors can act like electronic switches, turning currents on and off much faster and more efficiently than mechanical switches. This is crucial for digital circuits, where transistors act as tiny switches that represent the zeros and ones of digital information. Section 10. Biasing transistors, setting the stage. Finally, let's talk about biasing transistors. This is a crucial step in ensuring that our transistors function correctly within a circuit. Just like we need to bias a diode to make it work properly, we need to apply a similar concept to transistors. We also need to bias transistors to ensure they operate in the desired region of their characteristics. This involves understanding the different regions of operation, such as the cutoff, active, and saturation regions. Biasing involves setting up a specific DC voltage and current level at the transistor's terminals, using external components like resistors and capacitors. These components help stabilize the operating point of the transistor. Proper biasing ensures that the transistor amplifies or switches signals accurately and efficiently. Without correct biasing, the transistor might not function as intended, leading to signal distortion or even circuit failure. So there you have it, a whirlwind tour of diodes and transistors. These components are fundamental in the world of electronics. These amazing semiconductor devices are the foundation of modern electronics, enabling us to communicate, compute, and control the world around us. They are found in everything from smartphones to complex industrial machinery. From the simplest diode rectifier to the most complex integrated circuits, These components play a vital role in the functionality of electronic devices. Diodes and transistors are the unsung heroes of our digital age. They work silently behind the scenes, making sure our devices run smoothly and efficiently. Without them, the technological advancements we enjoy today would not be possible.